Okay. So welcome. So this is the section that's going to be on electric circuits. We break it down into a couple of bits. There's simple circuits, and then there's something called Kirchhoff's law, which is actually for more complicated circuits, but it's very formulaic. It's very processed, so people can usually do quite well on it. And then there's a couple of other bits, so we'll just work through it. I want to talk to you about resistance in series and parallel. We've talked about series and parallel before when we did capacitors. And it's the same terminology. So here I have my battery or my cell. If there's one of them, it's a cell. If there's a bunch of them, it's a battery. And here's a switch. This is an open switch, which means that no current can flow. If it's closed, you just draw it like that. You try and show that it's there, but you kind of like show it like that. And then we have two resistors. This is the international system for the resistor, but the American system is that, just squiggly line. And it kind of gives the impression of it's tough getting through all those chicanes. It's kind of quite descriptive, really. And the reason why this is series is because there's only one route through this part. You've got to go through the first as a current before you can go through the second. There's no junctions. If we compare that with the parallel, we have a junction here and a junction there. And what's happening is that the current of current is splitting. And in splitting, some of the current goes one way and some of the current goes the other way. But the current at the top is the same as the current at the bottom, which is the same as the total current passing through the two resistors. So think of current as like water flowing through pipes. The water flowing through the left-hand pipe plus the water flowing through the right-hand pipe has to equal the water flowing out of my pump. And the water flowing out of my pump has to equal the water flowing into my pump. So, and then think of voltages, potential differences, like pressure differences. And so the wire is like a really big, fat pipe. And you can't have a pressure difference on a really big, fat pipe. And so, if you like, the pressure there is the same as the pressure there because they're connected together just by this big, fat pipe. And the pressure there is the same as the pressure there because they're connected together by a big, fat pipe. So the pressure difference across R1 is the same as the pressure difference across R2. And so people learn these like terminologies. The current splits, the voltage splits in a series network, but the current is the same. And the current splits in a parallel network, but the voltage is the same. So you see that? And it's really worthwhile going back and just trying to visualize it as water flowing. Think of the battery as like a pump, and think of the wires as big, fat wires, and then think of the resistors as little straws. That's where all the pressure drop takes place. So this is a water flow analogy for this circuit. It is, on simple circuits, it's the conceptual understanding that catches you out. There'll be some concept you don't see, or there'll be some concept you make a mistake of. The math is very simple. It's just V equals IR for the most part. But it's the concept that's the issue. What we say is for a series, the same current flows through all resistors in a series network. The voltage drop across each resistor adds in series. So I got to add these things. The voltage drops in series because I add the resistances in series. The Parallel, well, we say the current through each resistor in parallel network adds, so the two currents add up to the total current. The potential difference across each resistor in a parallel network is the same. Just by the by, used to be when you had Christmas tree lights, they were wired in series, just the way they used to do it. And every winter holiday, you would get out your Christmas tree lights and you'd plug them in, and they wouldn't work. And you'd have to unscrew each light in turn and replace it with one that you thought was good, in the hopes that there was only one broken light. And if there was, and you replaced it with a good one, all the lights would light. If there was two broken lights, you would have to get two lights. And can you imagine the combinations of 2 into 13? It was hopeless. And if during the holidays one of them stopped working, they all stopped working. You had to find out which one it was. And then along came the more expensive lights, and they basically wired them in parallel. And if you have one wired in parallel, yeah, this can be disconnected, and the current's still going to go through the other one. And so one light won't work. You just replace the light that doesn't work. By and large, though, we use parallel and series in combinations to get the resistance that we want. Most of the time, resistors are not used to limit current. Most of the time, resistors are used to get the voltage that we want onto the component that we want. So if this is an LED or a lamp, if that's a lamp, and that lamp can only stand, say, 4 volts. If you put 5 on, it burns out. And this is a 6-volt battery. What you do is you try and make it so that that has 2 volts across it, and that has 4 volts across it. So you're using this resistor down here as a way of controlling the potential difference across the component that you want to actually have do something. So the resistors are kind of like the kind of ways of controlling voltage drops. And I've never read that in a book, but that's just my intuition from playing with circuits is, why am I doing this? Oh, I think I'm doing this more often than not to actually control voltages. I can think of some circuits where I need a resistor to control my current flow, but I think my bias is they tend to be the high power circuits. And these days, most circuits tend to be signal processing circuits. I think in the world we have more signal processing circuits than we have high power circuits. And it didn't used to be that way. You know, it used to be that we had more generators than we had, well, more TVs for sure, and maybe even more radios, although radios came across pretty quick. So electronics came up after electricity, if you like. Okay, so there's the fundamentals. So I learned this with resistors, and then I learned about capacitors. So I learned the equation for resistors, and then I do the opposite for capacitors. If you learned it the other way around, like if you're doing it with me for the first time, and you learned about capacitors first, then you learned that you add parallel capacitors, kind of like just in, what you learned was CP is equal to C1 plus C2, and now you're learning that 1 over RP equals 1 over R1 plus 1 over R2. And you learned before that that 1 over CS equal 1 over C1 plus 1 over C2, and now you're learning that RS is equal to R1 plus R2. They're the opposite methodologies, and I just learned it. It makes sense. I can show you why it makes sense. But at some point you have to remember it. So you learn it for one and you remember the others the opposite way around. Okay. So an 8 ohm resistor is connected in series with a 4 ohm resistor. What is the equivalent resistance of this network? Can you do that for me, please? Let's get those brain cells going. So this is a 8 ohm. This is a 4 ohm, and I want R series is equal to, I got something like 24, 25 people. Very good. Let's move on. Good. Very good. Very good. Very good indeed. Is that the seconds that's going? Oh, it is. Sorry. I was thinking, man, they are flying. So, let's go. As always, I can't tell if you're going to do it or not. So if you're not going to do it, just click in anything, and I won't wait for you. But part of the clickers is to slow me down. Because when I'm free running, I would give you about 40 seconds to do this, and I'd be out. And I realize that means that a lot of people are just like realizing that he's never going to give me enough time. So at some point, it makes sense that you stop trying, and I think everybody's fine, you know. So I'm going to wait a few minutes longer, a few seconds longer. Like 23 people. Question or comment?
I think some people may not have pressed the turn their answers real quickly because these questions aren't on the notes. So.
Oh, are they not? No? Okay, well, it's okay. Write them down. Sorry. Has that happened before? Is that this class? Is this class that I have the old version or something? I'm so sorry if you just try and tell me at the end of the lab, and I'll try and go to my office and change them straight away. Otherwise, I won't change them. Oh, it's in this room. I need to change them. That's the issue. I'm so sorry. I know that's frustrating. Okay. I'm going to stop here. And most people are saying C, so let's have a see if that's right. And we're going to say, well, in series, our series equals R1 plus R2. So our series is equal to literally 8 plus 4, which equals 12 ohms. 8 ohm resistor is connected in parallel. Oops, it's 4 ohms, sorry. And what is the equivalent resistance to this resistor network? So can you ever got that for me, please? So our parallel equals. So let's pause it there. And what do most people say? Most people say, oh, mainly B with a little bit of A. So what's going on here? Oh, yeah. So in parallel, of course, we've got to add inversely. So 1 over Rp equals 1 over R1 plus 1 over R2. So 1 over Rp is equal to 1 over 8 plus 1 over 4. So 1 over Rp is equal to 1 over 8 plus 2 over 8, because I want a common denominator, which equals 3 over 8. So Rp is equal to 8 over 3, which equals 2.66 ohms. So it's B. And that was the most common one. A, I suspect if you look at A, it is 3 over 8. Am I right?
Yep.
And what happens there is that people are forgetting to flip the thing back. So here's two issues. One is set an alarm, because that's a very common mistake. So resolve. I am not going to give points away for that mistake. But secondly, if you look at your work, I suspect you're writing this down but not that. And I suspect you're writing that down but not that. And I suspect you're writing that down but not that. And so you get this 3 over 8, and there's nothing to tell you. You need to flip the answer, because you're writing in phrases, not in sentences. So try and train yourself to write in complete sentences. So 1 over Rp equals that. And then you're much less likely to make a mistake like that if you're writing the 1 over Rp. And it's that next level of mastery. It's like, you know, your math is fine. It's not about math. This is about dotting all the I's and crossing all the T's as far as the process is concerned. And it's, you know, like learning the ways that enable you to do less mistakes. So try and remember, if I write more in sentences, it doesn't take me much longer, but I catch these mistakes. So it's really useful. I apologize for this. This is something that I messed with a long time ago, and I didn't realize it was here. And I can't erase it now. That's the strange thing. But this is a more realistic test question, which is a combination of series bits and parallel bits. And what we can do is I can go on to another page to do it. It's 3, 8, and 2. So let's go over here. And I'll go here. Oh, okay, thank you. So it's going to be this is 3. Oh, come on, you don't need to do that. This is 3 ohms. I think this is 8 ohms. I think this is 2 ohms. Is that right? Okay. So the problem with this is it's like eating spaghetti where, you know, do you begin in the left-hand side or the right-hand side, or what do you do? And it's like, you look for the unambiguous bit. So I look at this and say, well, the 8 is in series with the 3, but, you know, so is the 2. And it's like, man, there's that junction there and all. So I'm going to do that bit first. Now, I don't want you to have the idea that you're always going to do the parallel first, because I want to show you this. Kind of same resistors, just connected up differently. In this one, I would do the series bit first. And I find it hard to articulate to you exactly what I'm doing. I'm looking, in my mind, I'm looking for the unambiguous bit, the thing that's definitely in something with something else. So you got to figure that out. And this is what makes this hard. It's called simple circuits, and it's sort of like, it's like rubbing salt in the wound, because they're anything but simple. So I want to, sorry, I didn't mean to do that. So I'm going to do this. I go like this. And I go, it's parallel. So 1 over Rp is equal to 1 over R1 plus 1 over R2. So 1 over Rp is equal to 1 over 8 plus 1 over 2, which equals 1 over 8 plus 4 over 8, which equals 5 over 8. So Rp is equal to 8 over 5. So then I go, well, there's my 3 again, but now I've replaced these parallel combinations with an equivalent resistor, which is 8 over 5 ohms, and this is 3 ohms. Let's write this out as 2.4 ohms. Okay, so I go R series equals R1 plus R2. R series equals 3 plus 2.4, which equals 5.4 ohms. So this thing boils down to one resistor, which is 5.4 ohms. Cool. Is it 1.6?
Yeah.
Oh, yeah. I shouldn't be laughing, should I? It's like thank you. At least as it shows it's live, it's like, you know, and I don't rehearse these things outside the room. Maybe I should. Thanks. Yeah. So there could be a network which is a combination of series and parallels, and I want to play with that just a little bit. So So I've shown you two of them. I've shown you that and that, which is basically in my mind is the same as that. Agreed? Which in my mind is the same as that is exactly the same as that. Exactly the same. That's that resistor, that's that resistor, that's that resistor. There's a junction, there's a junction, there's a junction, there's a junction. So the way, I think about these things, it's almost like the wires are elastic. And you can move the resistors around and the wires just go with them. So don't learn this pattern, and if you see anything else, say, I can't do that, I've never seen this before. Because, they're kind of like in combination. So, and this one down here could be, it just goes on. You sometimes see nasty little things like this. And if you did that, you'd go, well, let's have a look. There's a junction. That goes like that. That goes like that. Oh, these two guys are in series, so that goes like that. That goes like that, and this guy comes off the bottom. So A is A, and B is B, and then C is C, and D is D. And do you see what I did? I used that junction as my navigation point. And by using those two junctions, I could see that this C was in parallel with both of those. And then that was off the bottom. So this takes time. It's kind of like it's just something that as you play with, you'll get better at. Okay? Cool. So that's what we're doing here. And then, nice if there was an answer on that one. Well, we'll skip it. Oh, so this is the next level. So the next level is, look, a 12-volt electromotive force is applied across this. What is the current flow through the 2 ohm resistor? Now, I need some terminology. And the terminology I'm going to use is that the current through 2 is I2. The voltage across 2 is V2. The resistance of 2 is R2. I'm going to use that terminology. It's not the best, but it kind of works for me, okay? And my credo, my guiding principle is I try to solve things in one step. This is a long calculation with a whole bunch of steps. They're all simple steps, but there's a whole bunch of them. So let's begin. I'm going to say find I2. That's what it wants, the current flow through the 2 ohm resistor using I2 equals V2 over R2. Isn't that Ohm's law? V equals IR. Let's solve it. Oh, I don't know what V2 is, but I know R2 is 2. Now, I should be clear. I don't know what V2 is, do I? I don't know what V2 is. I know between the top junction and below the 6 is 12 volts, but I don't know what that value is. Okay. I'm going to say, well, this is not so bad. Find V2 using, now I've got to put my thinking cap on here, because it's tempting to say, well, use Ohm's law. And I'll say V2 equals I2 times R2. But can you see the problem with that? What's the problem with that? Yeah, I don't know what this is. And didn't I just use that equation? I2 equals V2 over R2. V2 equals I2 times R2. It's the same equation. I'm going round in a circle. And that's not going to get me anywhere. So, although it's a true equation, it doesn't progress me anyway. So that's not going to take me very far. So I have to put my thinking cap on. All right, so I can't get it using Ohm's law. Is there another law I know? And there is another law I know. I know that the EMF is equal to the potential difference across the top, which is V2, plus the potential difference across the bottom, which is V6. The 12 volts is equal to the PD across that 2 plus the PD across that 6. Now, I've ignored the 4 because the PD across the 4 is the same as the PD across the 2. It's not in addition to it. It's like the same as. You know, it's like I have a staircase, and the staircase goes like that, and then there's a balcony, and there's a staircase there, and a staircase there. And the height is the height of that staircase plus the height of that staircase. I don't worry about this staircase. It's not addition to it. It's parallel to. Do you see the analogy? So, okay, that's a bit of progress. Problem. So let's put some numbers in. So EMF, I know the EMF is 12 is equal to V2, that's what I want, plus, oh man, I don't know V6. So let's just go to the next level. V2 equals 12 minus V6. At least I'm ready. Yeah, let's at least rearrange it so I get V2. If only I knew V6. Oh, find V6 using V6 equals I6 times R6, which equals I6 times 6. But I don't know I6. Find I6 using I6. I've used Ohm's law, so that's not going to do any good. Oh, I know. What can you tell me about the current flow through the 6 and the current flow around the circuit? Same, aren't they? So I6 is equal to I system. This is a good sign. Because I've gone out and out and out and out. And now I'm looking at that. And I go, I system is equal to V system over R system. And I know my V system is 12 over R system. Still not there, but I'm getting ever closer. Didn't I do this in the last problem? R system, let's do this, let's go over here. So I'm going to do that bit first. 1 over RP equals 1 over R1 plus 1 over R2, which equals 1 over 4 plus 1 over 2, which equals 1 over 4 plus 2 over 4, which equals 3 over 4. So RP is equal to 4 over 3. Glad I didn't make that mistake again. So now I have 4 over 3 ohms, and this is 6 ohms. RS is equal to R1 plus R2, so RS is equal to 1.33 plus 6. RS is equal to 7.33 ohms. Cool? I'm as deep as I need to go. I can't go any more broader. Oh, I'm sorry, I need to do that. I want to go down here. I want to change my color now. And now what I do is I work back. I go, let's take that back here. So this equals 12 over 7.33, which equals, and I'll dig out my calculator. So that's going to be 1.64. And it's going to be amps. And then I go here and say, well, okay, that was I system, so I6 equals 1.64 amps. And then I go here, and I go, so this is going to be times 6 is going to be 9.82, and this is a voltage, so that's volts. So then I take that to there, and I go, this equals 12 minus 9.82, which equals 2.18. And then that means that that goes here, and that equals 2.18 over 2, which equals 1.09 amps. There we have it. So what do you think? V equals IR. EMF equals the sum of the potentials. I system equals the I of the series bit. It's not hard mathematically, but it's not an easy question. It's not easy because it's not obvious when you do what. It's not easy because there are probably 3 ways to solve this problem. That's, 3 obvious ways to solve this problem. It's not easy because it's going to be a fair amount of effort to master it, and yet it's just one problem in the end, So it might seem a lot of work, but if you're going to do electrical engineering, you've got to pass through this way. And it does get easy with practice. There are some shortcuts. So let me talk about that a little bit. I can tell you, for example, that if I have a 4 and a 2 ohm resistors in parallel, then if I add them together, I get 6. So, and then it switches. The little resistance adds the big current. So I want to go to a different color because I don't want to get this confused, because this is just a little bit of an insight that you might, with experience, like. So what I'm going to say is that that 4 and that 2 combine together to give me 6. So I can say that 2/6 of the current go through there, and 4/6 of the current goes through there. Because that's the inverse ratio of the resistors. And sometimes with voltages, you can split the voltage. Again, you add the two resistors together, and then you say, okay, then this will drop so many. If it's a 2-to-1, let me illustrate those 2 points. Let's say I have, just call it out. Just give me 2 resistors. 12 and 30. And let's say, give me a voltage. 45 volts. 45 volts. So you want to know the voltage on each one of these? What you do is you say, okay, I have 45 divided by the total, which is 42. That's how many volts you get per ohm. Oh, so times 12 equals V top. 45 over 42 times 30 equals V bottom.
It's just our current times the...
Pardon?
It's just the current.
No, it's not the current.
That'd be current in the system. Times ohms.
No. Because the current is going to be... Yeah, it's the current... So, yes, I'm sorry. That's the current multiplied by that voltage, yeah. But can you see, I'm not even thinking about it in terms of current. I'm just thinking about it in terms of ratio. Just a ratio, yeah. So you can do things with ratios that save you some calculation. But I think that comes as a next step. The thing that I think you should aim to really feel comfortable with is this. And then get clever with doing ratios to save time, okay? I can guarantee you there'll be something like that on the test. So get ready for it. This next thing will also be on the test. If I have time for questions, it's like I'm running out of space. So there are some circuits that have several power supplies in. Frankly, I've never dealt with one, but I don't know if any of the electrical engineers have dealt with one. Have you guys dealt with anything like that? I've never dealt with anything with 2 power supplies, but they exist. I know they exist. And the analysis does not lend itself to Ohm's law. So we have to find a way of dealing with it. And what you'll learn is that we learn Kirchhoff's rules, and then later on you'll learn Thevenin's theorem. And it kind of goes on. So we're going to do Kirchhoff's rules. It's a way of dealing with more complicated circuits. You can apply them to simple circuits, but they tends to be a bit long. So we have 2 rules, the junction rule and the loop rule. Let's have a look at our circuit. There's a typical, that's a typical circuit. Couple of power supplies, some resistors, couple of loops. What we find is that at a junction, the current in equals the current out, because you can't create or add electrons. So that's a statement of the obvious. And what you find around a loop is that the sum of the voltages equals 0. Because what you create, you use up. Yeah? Now, we've always got to be a bit careful with our with our sign conventions. So if the loop exits, so I've got to go to this next line. I'm sorry. Let's look at this. So this is my power supply. This is a resistor. I am imagining a current to flow. I've decided the current flows in this direction. On this circuit, it makes sense, but it does not matter. As long as I am consistent with my nomenclature, I can have the wrong direction for current and the problem will still work out. So I have to decide on what direction my current flows, and I have to decide on what direction my loop loops. What is this loop? This loop is a point of interest. I really want to draw it going through the wire, but it makes the diagram too complicated, so I show it in the middle of the thing. It is a way of keeping track. It has not got any physical reality whatsoever. It's a way of making some things be positive and other things be negative. It's a way of keeping you consistent. So don't try and get a physical understanding for the loop. It's just the loop. And the rule is, if the current, not the loop, if the current has the same sense as the loop, well, sense meaning direction. My current is going in that direction, and my loop is going in that direction. My current is going in that direction, and my loop is going in that direction. That's always going to be the case. Well, not always. But then the potential difference across the resistor, my current is going downwards and my loop is going downwards, is negative. So when your I and your loop flow through a resistor in the same way, then VPD is negative. If I choose to put my loop in the opposite direction so that my current is flowing down and my loop is flowing up, then VPD is positive. Okay, so I've figured out the sign convention for my potential differences. I need to figure out my sign convention for my currents, for my EMFs. And for that, I go back here and I say, if the loop exits the voltage source through the positive terminal, then the EMF is positive. Unfortunately, this should all be on one page, I'm sorry. So look here, my loop is exiting via the positive terminal. EMF positive. My loop is exiting via the negative terminal. EMF negative. Two rules. Two sign conventions. Let's do one. First thing, pick a junction, doesn't matter where. Three wires, three currents. I1, I2, I3. How do I know? I have no idea. I just made it up. I have some current coming in. I have some current going out. I give it names. Here's the problem with this sign convention. I2 does not mean the current through resistor 2. And I don't know a way around that. It's just it works great for the previous thing. I2 means the current through 2. V2 means the voltage across 2. R2 means the resistance of 2. And then I get here, and I suppose I could go I9, I10, and I11, but, you know, maybe there's a 9 ohm resistor there. So it's just a bit, I don't have a good way around it. It's a different context, so a different terminology. I1 is simply the current in this piece of wire, and I2 is the current in that piece of wire, and I3 is the current in that piece of wire. I don't know any other way to deal with it. But it's still going to be 1, 2, and 3. So that's, and it's the numbers I'm worried about. I suppose, I've not tried it, but maybe that would work, you know, I suppose. But let me live with it, because I know this works at the moment, okay? So I could have put anything back, but what I got to do is I got to write down my junction rule. So junction rule. Junction rule is I2 equals I1 plus I3. Does that not make sense based on my diagram? I got I2 coming into the junction, and I got I1 and I3 leaving the junction. So there's my junction rule. That's the first step. Then the second step is you decide on a loop direction. Now, I'm going to keep the same clockwise direction in the second loop. I don't suppose I have to, but I am, just because I just get used to doing it. There's also, by the way, a third loop round the outside, but I'm not going to mess with that. I'm going to mess with these two. I only need two of them. So loop rules. Can you please write me down what you think the loop rule is for this left-hand junction, for this left-hand loop? Can you write it down for me? You're gonna look at your EMF, and you're going to decide, is that a positive or negative EMF? You're going to look at that resistor, and the potential difference will be I times R. And what is the I through this resistor? What's it called? What have I called it? Look around your diagram. What have I called the current flowing through that? I1, because I1 goes like that. So it's going to be I1 times 3, because V equals IR. And then this guy here is going to be 7 times the current flowing through it, which is I2. But what are their signs? So write me an expression which has an EMF and a potential difference for R3 and a potential difference for R7, and they sum to 0. So try and write me down that equation. You had a question or a comment?
That question. I understand that the electrons follow the path clockwise on the left side, but on the right side?
No. Sorry, no. So I'm stopping you. I'm sorry, I shouldn't cut you off, but on the left side, do you mean the current, or do you mean that loop?
The loop, sorry.
So the loop is not electrons. It's just imaginary. And I decided to make it go in that direction. There's no indication from the circuit. It's not because I'm looking at my voltage source and saying, oh, that must go that way. It is just bookkeeping.
So that's why it's the same thing on the other side.
Yeah, so I'm going to tell you, this is what the rule. Always put it clockwise. We don't. You know, why? Because I'm telling you. You know, and it will work. But in truth, you can do it any way you like, as long as you're consistent, you know. So any progress on this? Let's have a look. I'm going to start you off. It's going to be +6 for my EMF. Yeah? I looked at that EMF and it's 6, and I decided it was a +6 because, what's the rule? What was it that left via the positive? Was it the current or was it the loop? The loop. The loop left by the positive, so +6. Plus, let's do the 3. It's going to be 3I1. Is that a positive or a negative 3? I1, loop, same direction, minus 3I1, added to, what about this 7? It's going to be 7I2, but is it going to be positive or negative? Negative, because the current's flowing down and the loop's flowing down. Okay? So the two rules are, if the loop leaves the battery via a negative terminal, it's negative, and if it leaves via a positive terminal, it's a positive. What terminal does it leave by? And then for the potential differences, if the current flow that you decided and the loop that you decided are in the same direction, call it a negative potential difference, and if they're in opposite directions, call it positive. With that in mind, can you do the next one for me? So let's look at the second loop. So it's a 9 volts EMF, and is it a positive or a negative 9? It's negative because it leaves, the loop leaves via the negative terminal. And then we add on to that, and I'm going to look at, doesn't matter, I'm going to look at my 5 ohms next. It's going to be 5I3. I3 goes all the way around that bit. And I3 is going in that direction at the top. It's going to the left, to the right along the bottom. It goes up the page, and it goes to the left along the top. So my I3 is flowing to the left, but my loop is flowing to the right, opposite direction, so that's a positive. And then I look at my I2, my I7. My I7. My 7 ohms. It's going to be 7 I2 again. And in this case, my current is still flowing down, but now my loop is flowing upwards. Now, how do you solve it? 3 equations, 3 unknowns. You know, talk to Professor Soash or something. No, there's a way. This is the way I do it. I say, oh, look, let's change colored pens. Oh, it's not doing what I thought it would do. Isn't that interesting? Isn't that weird? Well, okay. Now it's let me do this. It's kind of weird. Okay. So let's go down here to red. So what I'm going to do is I'm going to turn around and say, okay, well look, this has got this is I1 and I2, and this is I3 and I2. And this has got I2. And, oh, I know what to do. Let's get I1 in terms of I2. So get that in terms of I2. And then here, let's get that in terms of I2. And then I've got an equation that only has I2 in it. Yeah. So I'm going to come along here, and I'm going to go, I want to get I1. So I1. So I turn around here and I go 6 minus 7I2 over 3 is equal to I1. I left my 6 alone. I left my 7I2 alone. I took my 3I1 to the other side, and I divided by the 3. Now look at this guy. And for this guy, I want to get I3 by itself. Is that right? Yes, I want to get I3 by itself. So I'm going to come along here, and I'm going to go 9 minus 7I2 over 5 is equal to I3. So I said 9, took it to the other side, minus 7I2 to the other side, divided by 5 equals I3. So now I take these two guys, and I substitute them into I2 equals I1 plus I3. So I2 equals, I1 is 6 over 3 minus 7 over 3 I2. Added to I3 is 9 over 5 minus 7 over 5 I2. So I2 plus 7 over 3 I2 plus 7 over 5 I2 is equal to 6 over 3 plus 9 over 5. 15 over 15 I2 plus 35 over 15 I2 plus 21 over 15 I2 is equal to, might as well keep it in 15s, hadn't we? So that would be 30 over 15 plus 27 over 15. And now I can forget about my 15s because everything's got 15 in it. So 15 plus 35 makes 45, 50. 71 I2 is equal to 57. So I2 is equal to 57 over 71, which equals 57 divided by 71 equals 0.8 amps. Now, so you see where that came from. That's just math. So now that's I2, and what did I want? The current through the 5 ohm resistor, which is I3. So I say, okay, I3 equals 9 over 5 minus 7 over 5 I2. So I3 is equal to 9 over 5 minus 7 over 5 times 0.8, which equals 7 divided by 5, enter, times 0.8, enter. And then I go bracket 9 divided by 5, bracket minus second answer. I'm getting, that'll make sense. I'm getting an answer. I'm running out of time on my video, so I'm gonna stop it at 0.68. Okay. Is it positive or is it negative? According to your calculation. If it's positive, it means you guessed right. If it's negative, it means you just guessed the wrong direction. I'm gonna end it there for this tape.